Let me share the screen. So can you all confirm once, guys, whether my screen is visible? And what about my voice? Is it audible to everyone? Okay, great, guys. So thank you for quick confirmation. So we have left with 3 more minutes. So in another 3 minutes, I'm going to start today's session. So today we are talking about one of the important topic that is on distributed programming. So last class we have discussed about distributed concept, right? So today we are discussing more on distributed programming. Okay. So please inform to your friends. Guys, is it okay if I take extra class on next Saturday? So I will try to cover sixth session on next Saturday and the seventh session on next Sunday. Is it okay for you all, guys? Because we are lack with network extra class 11 to 1. So I'm going to take at the evening. I'm not going to take at morning, guys. So I'm going to take class from 6:30 or 7:30. We already have. Which class you have next week? Jyoti, which class you have? At what time? Network. What time? 11 to 1, right? So I'm going to take at 6:30 onwards. Uh, Hima Bindu, try to understand. I have to complete one more session before your examination. No, I will take class for 2 hours because I have to complete HDFS concept. So it is more practical, guys. So I'm not going to bore you by giving some theoretical concept. So it is more about practical. So I need 2 hours class on Saturday. Cloud computing 8:20 a.m. No, not on Saturday. Not on Saturday. So I'm taking it on. So not on Sunday, guys. I'm taking it on Saturday. I know Sunday you have 3 classes, but I'm taking it on Saturday. Saturday, one extra class I'm taking. So that too at evening. Weekdays, I think it is not possible for all, Tanya. What majority people are saying? Is it okay for all, guys? So I want to go with majority people. So Saturday evening, yes. It is fine, right? Okay. Thank you all, guys. I will go with majority. Okay, yes, guys, let's start with today's session. So let me show my screen. So hope my screen is visible to everyone. Is it visible, guys? Shall I get confirmation? So is my screen visible to everyone? Okay. Guys, actually, last class, as I told, so we have touched upon distributed system concept. And today we are going to get our hands dirty with the distributed programming aspects. Okay. So think of it as moving from the what to how. Okay. We will learn how to actually write programs that can run across multiple machines to process massive amounts of data. Okay. This is where the real power of big data systems comes into play. Okay. And yes, this is the agenda of today's session. So, or we can call it as roadmap for today's session. It is packed with some really critical concept. So I request each and everyone to pay your attention. Your attention is very, very important. Close attention is required today. So first we'll start with top-down approach. Okay. And then we will explore the various types of parallelism. Then we will dive into the heart of today's session, that is MapReduce programming model. After that, we will see how a MapReduce program works using Hadoop system. And finally, we will discuss iterative MapReduce. Okay, so it is going to be fantastic journey, guys. So ready to jump in? Are you all ready to jump in, guys? Can I get a message READY in chat box once you people are ready for today's session? Can I get big ready and chat box from each and everyone? Okay, guys. So now let us start with the very first topic, top-down design. Okay, in a what sequential context? See here, clearly I've mentioned in a sequential context. So think back to your first programming classes. So when you had a big complex problem, so what was the first thing you were taught to do, guys? You would break it down into smaller and more manageable sub problems, right? So this is the essence of the divide and conquer concept, divide and conquer approach. Correct, no? So you create a main function, and inside, see, you create a main function, and inside it, you call a series of functions like F1, F2, F3, F4, and F5. So that subfunctions solve each subproblem one after another. Okay, let me take one small example to explain on this. So imagine you are writing a program to process customer order. Okay, customer order. Okay, so you might have one functions to validate customer details. So this is one function you very much required, and another to check product inventory. Okay, so this function is checking product inventory. And one more function, the third process is on payment. So you are going to run separate program on payment. And fourth, generate the confirmation mail. Confirmation mail. Okay, guys, in a sequential program, you call these functions one by one, right? First, you will call validate function. Next, you will call product inventory, payment, and confirmation mail. The main function is the topmost one. Okay, and it divides the problem into sub problems, and it is simple and also intuitive. Guys, in this context, the programmer has a lot of freedom. So you can define a subproblem in a way, in any way that makes logical sense to you. Okay. The key is that each subproblem is executed one after another because we are using sequential context. Correct? No? So this is very natural and straightforward way to approach programming, but it has limitations when dealing with massive data sets. And as the total execution time is the sum of the time taken for each subproblem. Correct? No? You're all agreeing with my point. Now let us see how this same idea changes when we move to the parallel world. So it is not as simple as just calling function. Correct? No? So let us check with the next methodology. Okay. So that is top-down approach with respect to parallel context. So this is very, very important slides, guys. So this is very, very important slides. So please pay close attention. So when we move to a parallel context, the rule of the game change completely. Okay, the first and most crucial point is that, so we cannot simply decompose the problem into subproblem in any way the programmer chooses to. Correct? No? So we are not just organizing code, we are organizing work for multiple processors. So you have to think about the physical resources you have. So what and all key considerations we have to follow here? The very first key consideration is each subsystem, each subproblem needs to be assigned to a processor. So this is not just a mental model, guys. So it is a physical reality. You need to write your program in a way that allow different parts of the work to be sent to and executed on a different machines or cores. And then what is the primary goal here? The primary goal is to get the program to work faster. Guys, in your parallel designing, okay, in parallel design does not speed things up. You might as well as stick with what sequential programming. Parallelism for the same of parallelism is useless. Okay, so you must divide the problem only when you can combine the result at the end. Try to understand this. So simply we are not going to divide the program. Okay, so to get the final answer, see, suppose we have to get a final answer, means then only we can divide the entire problem into sub problems. So this is a conquer part. This is a conquer part. Conquer means what, guys? You are going to combine, right? So this is a conquer part. You are going to combine part of divide and conquer. And if you cannot merge the result from your parallel computation, the whole exercise is pointless. Okay, you need to decide. You need to decide where to do combination. Okay, is the merging process parallel itself or is a sequential bottleneck? See, for example, if you have 100 processors, okay, if you have 100 processors doing a calculation, but one single processor has to collect and combine all the results, that one processor might become a huge bottleneck. So defeating the purpose of parallelism, right? So what I would like to say here is, in parallel system, the design process is not just about logical decomposition. So it is a strategic process that involves thinking about resource allocation, communication overhead, and final result combinations. So hope till here everything is clear. Is this clear to everyone? Shall I get CC and chat box once it is clear? Shall I get CC and chat box once it is clear to everyone? Okay. So now we are moving on to the another key considerations in the parallel design. Listen to me carefully now. This is another very, very important concept. Guys, so now we are talking about number of sub-problems, sorry, not system, sub-problems. So this is another area where sequential and parallel designs differ significantly. Guys, in a conventional top-down design for a sequential system, the goal is to keep the number of sub-problems manageable. Correct, no? Why this, guys? So why means, guys, the reason behind this is the programmer have to keep track of the flow of the computations as it progresses. Guys, you just imagine you are breaking a problem into 10,000 sequential functions. So would be what nightmare to manage, right? So you aim for a reasonable number of logical sub-problems. That is very, very important. Okay, that is what I have mentioned in the sub-point actually. However, in parallel system, the number of sub-problems is often dictated by the number of processor you have available. Okay, the goal is called as processor utilization. Processor utilization. Guys, if you just imagine, if you have n processors, okay, if you have n processor, you should ideally have at least n sub-problems. Correct, no? So that each processor has work to do actually. So if you only have one sub-problem for 100 processors, then 99 of them will be what still idle, right? Guys, if you have 1,000, okay, let me take 1,000 sub-problems for 100 processors. The work can be distributed among this 100 processors, and they can be fully utilized. So the more sub-problems you can create and distribute, the better you can use your available hardware and achieve maximum speed up. Okay, I got one question. Sir, by processor, you mean cores? Processor means cores also you can take. Processor means you can take separate system also. Okay, so cores you are considering means then we are going to call it as multi-core system. Okay, processor means the processor is nothing but a separate one. So which will be containing multi-core system. Okay, so multi-processor and multi-core both are not same. So both are different. So here I'm talking about processor. I'm not worrying about cores here. So is this clear, Priyanka? Priyanka, is this clear? Okay, now see, look at here. I was talking about 1,000 processor. I was talking about 1,000 processors with, 1,000 sub-problems with 100 processors, right? Okay, so again, I got a question from Priyanka. So then why n sub-problems for n processors? You just imagine, so we have a cluster. So in cluster, we have n processors. Okay, so I'm telling you, see, once you have n sub-problems, so n sub-problems are dividing into n processors means, then you can get a better result. That is what I'm trying to explaining you. So as I told, suppose you have one sub-problem and you have 100 processors means, see, for one sub-problem, one processor is enough, right? Then what is the purpose of using 100 processors? So that is what I'm trying to explaining you here. Sir, I have a question. If parallel program can be divided into n sub-problems, then how it is decided that how many sub-problems a program can be broken? So that is depends on the program what you are going to write, Ravi Kumar. Okay, so here you just look at here. So this is the main function. So this main function is containing 7 different functions. So each function is called as a separate sub-problems. So suppose I have 10 processors means, so all this, see, function 1 can distribute to processor 1, function 2 can distribute to processor 2, function 2 can distribute to processor 3. You're understanding my point. So we should see, this is the minimum condition I'm telling you. So n sub problems we have means we should have n processor means then it is good. Or else we can take, see here I've told you, right, 1000 sub problems we have here. So 100 program, 100 processor, this is also okay. I can utilize this complete 100 processor. That is what I'm trying to explaining you people. So hope everyone understood this. Ravi Kumar, this is not the job of a programmer. This is the job of system. Okay, that you will experience later. Okay, that you will experience later. So as a programmer, you should have this knowledge. That is what I'm telling you. That's it. You people are not going to do anything. So this job used to be done by the some other processor. One processor will take care of everything. So guys, you keep all this concept in your mind. So once I'm going to explain you MapReduce programmer, then you will understand. So why I'm explaining you all this concept. So is this clear to everyone? I got so many questions. What I mean is each processor can have multiple sub problems considering each processor as multi-cores. Yeah, that is also possible, Priyanka. So even see, that is multi-core system. So for each core, you can assign this function one. That is also possible. Otherwise, thread level also you can perform parallelism. So in Flynn's taxonomy, I have explained you, right? So thread level also we can do parallelism. Function wise also we can do parallelism. Priyanka, now you are understanding, right? So how programmer will know that how many processor a cluster will have? So why we have to worry about that? So why as a programmer we have to worry about that? So as I told guys, suppose we have 100 processor, leave it. Okay, that is the job of what? Some other processor. So this will take the number of processor available. So based on that, it will distribute the task. Why we have to worry about that? Suppose you are writing, see you, okay, Ravi Kumar, you just listen to me carefully. So now you are writing a program. Okay, that see in your computer, you have quad core system. So totally you have 8 cores. So in this situation, see, as a programmer, you know how many cores are available here, right? As a programmer, you know how many cores are available. So based on that, you can distribute your functions. That is possible with respect to single system. So now I'm talking about what? Now I'm talking about distributed computing. So in distributed computing, why we have to worry how many systems are there in a cluster? Okay, so we are going to utilize the total number of available processor 100%. That is what I'm trying to explaining you all. So is this clear to everyone? Yes or no? Ravi Kumar, you are asking this question. I think it is not by programmer. Yes, it is not by programmer. That you will understand later. See, this is the problem you have, guys. So you people are not wait till the end. That's why always you have to wait till the end. Suppose, yes, any complexity is there means okay. See, next coming slides, I'm going to explain you each and everything in detail. Ravi Kumar, you are not clear. So how can I clarify this? How can I clarify this? I'm telling you now, as a programmer, you're not supposed to know anything about how many processors are available. Understanding? Okay, you wait for a while. Okay, I will explain. So you try to understand this concept clearly. That's it, guys. So as I told, the more sub problems you can create and distribute, okay, the better you can use your available hardware and achieve maximum speed up. That you should understand. Okay, this is the key shift in mindset. So you are not just writing elegant code. Try to understand. I'm repeating this statement. You are not just writing elegant code. You are writing code that can efficiently leverage hardware resources. Okay, so now look at the visual representation of this top-down approach. You look at here, guys. So look at the diagram, friends. So this is great visual for understanding the top-down design in parallel context. The main problem P, so is at the top. The first step of the design is to break it down into sub-problems. Okay, that is, what are the sub-problems we have here? So we have sub-problem P1 and also we have sub-problem P2. The crucial part is that these sub-problems can run in parallel. Correct, no? So these two can run in parallel. So they are independent enough to be what assigned to different processor at the same time. So hope you are understanding now. And now look at the next level. So P1 is further divided into P11 and also P12. P2 becomes P21. At this level, P11, P12 and P21 can run all programs in parallel. So this shows the power of the design. At each step, so we are creating more and more opportunities for parallel execution. See, this is the classic tree-like structure. This is a classic tree-like structure. Okay, and it perfectly demonstrates the divide and conquer principle in parallel setting. So we keep dividing the problem until we reach a point where the sub-problems are small enough to be solved efficiently by a single processor. The key is to ensure that these divisions are done in a way that allows for maximum concurrency. Okay, to make this concept even clear, so let's look at some examples. Now with example, I'm explaining you all guys. Listen to me carefully now. So many of them have doubts in your mind, right? So now I'm going to show you each and everything with three problems. I'm not taking single problem. I'm taking three different problems. Okay, so now look at the problem statement given here. What is given here? So we need to find a key. So let's call that key as K in a very large sorted list LS. So this is list LS of size N. Okay, so now look at the data. Now look at the data. The list LS is not on a single computer. So it is stored in a distributed system with P processors. Try to understand. This entire list is not stored on a single processor. So it is distributed among P processors. Okay. So now you can tell me guys, each processor hold a chunk of the data, right? Specifically, N by P items. This is very, very important. N is nothing but total number of size of the data, and it is divided into number of processor available. So now you can think, sir, I have 8 cores. Then it will divide to 8 cores. Suppose you have 100 cores. Automatically it will divide to 100 cores. Suppose you have 1000 cores. So this complete data is divided into 1000 cores actually. So why you need to worry, guys? So based on the number of processor available, the data itself is divided into different processors. Understanding my point? Then what is the solutions to this? Guys, solution is a sequential approach would be to do a binary search on an entire list. Correct? No. So we are performing a binary search because we are trying to searching for the key element. So we can use binary search. So which would be why I'm choosing binary programming here? Because it will take log n time. Correct? No. So it will take big O of log n time. So, but since our data is distributed, we cannot do something much smarter. We can run a binary search on each of the processor in parallel. Okay, so each processor searches its own N by P chunk of data. So is there any scheduler kind of system like Slum or PBS who decides this allocation of? See, I'm teaching you the general concept, Ravi Kumar. I'm teaching you the general concept. Yes, we will be having scheduler there. So scheduler will take care of everything. See, once I'm started explaining a Hadoop concept, then you will understand. So a particular software name I can explain you there. Understanding? So now I'm talking generally. Okay, now I'm talking everything generally. So why you are assuming? So it is depends on what system to system, right? Okay, so listen to me. Okay, in middle you are asking some questions, means I will not give more number of examples. Okay, so try to understand this. See, this is n log n. Why we have selected n log n? Because n log n is the what? Fastest time actually. Then what do you mean by combination? See, we have distributed data among what different processors. See, we are performing what searching task. After performing searching task, so we have to combine all the result, right? So that is called as combination. That is called as combination. See, as soon as one of the processor finds the key, it returns its location. It returns its location back to the what? One of the processor. So the results from all processors are collected at the single point, perhaps at the what? Master processor. That processor name is called as master processor. So remaining all are called as what? Slave processors. Okay, so which then return the final answer. So then who is responsible of what? Performing all these tasks? That is the job of master processor. So now I think Ravi Kumar is understanding the concept clearly. Is it clear now, Ravi Kumar? Shall I get the confirmations from your end? Is this clear now? See, I'm naming it as master node. Right now, I'm not calling it as any software name. I'm not giving any software name here. Okay. Now look at the what? Speed up and time complexity. Guys, this is the most exciting part, right? Since all processors are working in parallel, the search time is no longer dependent on the total list size n. Okay, instead, it depends on the size of the chunks each processor has. What is this? What is the size of this chunk here? The chunks here, that is n by p, right? Then what is time complexity? Time complexity would be big O of log n by p. So the speed up is approximately p times. So n is constant. The speed up is approximately p times. So as you are doing the work in parallel on p processors. So this is the perfect example of data parallelism. Try to understand this. So data parallelism. So here we have distributed data among number of processors. That's why it is called as data parallelism. Okay, shall we take one more example to explain, guys? Shall we take one more example? Can you all quickly confirm on chat box? Guys, each and every question I'm reading on chat box. Okay, so now I parallelly opened on my mobile to check your chat box. I don't want to skip any of the messages, guys. Okay, so now look at the second example. So this is fingerprint matching. This example we have taken from fingerprint matching. Guys, listen to me carefully now. This is another beautiful example. Imagine, guys, a massive database of fingerprints, perhaps for a what? National Security Agency. You need to find a match for a what? New fingerprint. Okay, that new fingerprint is called as represented by capital F. Then what is the problem here? The problem is find a match for a what? Single fingerprint F in database of D. So in database of what? D print. So this is the problem. So this is the problem statement given here. Then what about data? Data is nothing but what, guys? The database is too large for one machine, right? So what we are doing here? So we are using distributed database. The meaning of this is it is partitioned and stored evenly across distributed system. See here, we have stored evenly. Try to understand this point. We have stored evenly. Okay. This, guys, actually, the data partition is static here. An infrequent activity. So done only when many new entries are added to the database. The search, however, is a very frequent activity. I think everyone will agree with my point. Then what is the solution to this problem? So we have understood about data. So we have understood about problem statement. Then what is the solution? Guys, the new fingerprint F is sent to all the processor in a distributed system. Correct? No? See, we'll send to this, we'll send to this, we'll send to this, we'll send to this. We'll send the what? The new fingerprint F to all the processors in a distributed system. And each processor then perform a what? Sequential search on its own partitions of the database to find a match. So hope you are all understanding. This is about fingerprint because we have distributed among so many databases evenly. Then what about speed up here? Again, guys, look at here. Just like a keyword search, this approach offers a speed up of P. The time complexity is what, guys? The time complexity of big O of N by P. So where N is the total number of fingerprints and P is the number of processor. Again, this is much faster than the sequential approach of searching of the entire databases. Correct? No, on a single machine. So which would take big O of N times. So this example clearly shows the power of data parallelism. So where we divide the data and apply the same computations on different part of your processors. So hope this example is crystal clear. Shall I take one more example to explain, guys? Shall I take document example to explain the same? Shall we go with one more example? Now look at here, guys. So I'm taking the third example. See, I'm not giving you one example, guys. I'm taking 3 examples to explain the entire concept of distributed system. So keep this point in your mind. So based on that, you are going to learn the concept. Okay. So now we are moving to the third example. Look at the third example, guys. So now document search. So we are talking about document search. The problem here is to find keywords from each document in a large distributed collection. Okay. What is that large distributed collection? Large distributed collection is called as capital D. Then what is the problem here, guys? So we have to find the keywords from each document D in a distributed document collection of D, actually, capital D. Guys, can you tell me about solution? Can anyone tell me about solution? This is very much similar to the previous example, right? Now what we are going to do, guys, the document D. Okay, the document D is distributed across multiple processes. Okay, look at here. So we have process P0, process P1, so on, process PP. So here some of the data is distributed, some of the data is distributed, some of the data is distributed evenly. Again, I have distributed data evenly. Each process works independently on its own subset of document. See, for example, P0 extract keyword from its share of the document. What is the share of its document? So it is started from 0 to N by P minus 1. Correct, no? N by P minus 1. So this is, see, in this range, it is going to search the data. And what P1 is going to do? So it will start from N by P to 2 into N by P minus 1. So the same thing will be what keep on going on. Then guys, what is the final answer? What is the final? So final is combination, right? Final answer is combinations. Once each processor has extracted the keywords. So one of the processor for an instance P0. Okay, you just imagine P0 is behaving like a master slave. So even it is behaving like a slave model, but still it is behaving like a master. Okay, so this will take the responsible of collecting all the keywords from the other processor to form a master keyword list. Okay, so this is another great example for data parallelism combined with simple conquer step. Okay, the work is divided based on the data and each task is identical. And the final step is a simple collection of the result. Guys, this model is very scalable and is the foundations for many search engine indexing system. So nowadays we are all using search engine, right? In search engine, we are using this concept. So now is this clear to everyone, guys? So now every doubts are clear. Each and every doubts are clear to everyone. Sir, how is P1 using N by 2? Look at here, man. Look at here. See, I have started from 0. I've started from 0 and where I have ended. So 0 to N minus P minus 1 I've taken. Then what is the next number? This is N minus P means what is the next number? This is one partition. Next number will start from N minus P, right? N by P, right? See here, it is started from N by P. Someone with a have you understood? You take real-time example, then you will understand. Okay, you take any numbers. You take 100 numbers. So then 100 is n, right? Then substitute the value and process the number and substitute the value. You'll get to know. So hope till here everything is clear. Okay, guys. So we have looked at top-down approach and some examples of how it is applied. Now let's formally define the different types of parallelism that we have been implicitly discussing. So that is the second part of our discussion today. Okay. So here, guys, we are discussing more on types of parallelism. So this will gives us a formal vocabulary to describe the different design pattern we just saw. So then we will get to the what star of the show, that is MapReduce, that we will discuss later. Okay, so let's start with the what next slide, data parallel execution model. Okay, guys, till here everything is clear. If you have any doubt, please ask me the question now. So I'm giving you time. So no doubts means I will move forward. Can I get confirmations from all guys? I'm looking at your chat box. Okay, fine. Yes, guys. Guys, look at here. So let's start with what? Data parallel execution. So which is the model we saw in our first three examples. The main idea here is that the data is partitioned and distributed across multiple nodes or processors. Okay, the goal is to create equal or balanced partition so that each processor has roughly the same amount of work. That is the intention. Okay, but the key principle is that all processors execute the same code in parallel. Guys, think of it like a group of people working on the same assembly line task, but each person is working on a different piece of the product. But what all people are doing, guys? So they're all performing the what? Assembly. So everyone knows their job, right? So they do it at the what? Same time. So data is different, but function is same. That is what I'm trying to explaining you here. So for an ideal scenario with homogeneous nodes, you just imagine. So we have taken homogeneous nodes. Homogeneous means what, guys? What is the meaning of homogeneous? Can anyone tell me? Why I've taken this term here? Machines with same processing power. Okay, machine with same processing power is called as homogeneous. Okay, and equal amount of work for each partition. Along with that, equal amount of work partition also we have done here. So the processor utilization will be close to what, guys? The processor utilization will be close to 100%. Correct? No? You're all getting my point. All the processors we are using here. That is the meaning, because equally we have divided. And also all the systems are homogeneous here. So however, this is not always the case, right? So should we get always homogeneous nodes in distributed computing? So there is a chance. So we'll get unbalanced data size or work, right? Or if you have heterogeneous nodes means, so some processors are faster, some processors are slower. So it will lead to higher overall execution time. Okay, the entire job will be held up by the slowest processor and a problem known as the straggler effect. Try to understand the problem. Straggler effect. See, some systems are very slow. Some systems are very fast. Then what the slowest system is going to take? So it will take a lot of time to complete the process, right? That problem is called as straggler effect. Okay, so data parallelism is incredibly powerful for problems where you can easily partition the data. and apply the same functions to each part. But what about problems where this is not possible? Correct? No. So let me take one more example here. So here I'm explaining the same. Okay, where data parallelism is not possible. Guys, this is one of the what beautiful example I'm explaining you today. So maybe you're all aware of quicksort, right? Are you all aware of quicksort? So how many of them aware of quicksort, guys? Can you all raise your hands? Otherwise, put a message in chat box. No, Priyanka, don't you know quicksort? No, sir. Okay, many of them are saying no. Okay, let me show you quicksort then. So this is the quicksort. You look at here, guys. So quicksort means we have an unsorted array list. So quickly, I'm giving you a glance on quicksort. So I have what unsorted array list. So here I'm going to pick one pivotal element. So that is based on the index value. So this is 0, right? This index value is 0. This is 1, 2, 3, 4, 5, 6, 7, 8. Totally, I have 9 elements. So in an array. So now we have to calculate pivot element. So how do we calculate pivot element? So pivot element means half of the element. So 9 by, how much it is? Half means 9 by 2. So 9 by 2 means I'm going to get 4.5. So here we are not going to consider fractional value. So instead of that, we will take 4 or we will take 5. So in this case, we have taken pivot element as 5. So now look at here. The data is divided into two parts, equal two parts. See, look at here. This is one part and this is another part. Including this is another part. Correct? No. So this is the way of what partitioning your element. And next, we are going to take the left side. Again, we are going to calculate the pivot element. Look at here. 0, 1, 2, 3 we have here. So 0 plus 3 divided by 2 we are going to perform. So that is 3 by 2 means 1.5, right? So we will take 1 or we are going to take 2 here. So again, we have partitioned this into two parts. Look at here. So we have partitioned this into two parts. So this is called as quicksort. So is this clear? Priyanka, you are getting some idea about quicksort. Priyanka and Himabindu. Okay, so now I'll come back to the problem. So what you have to observe here. So listen to me carefully now. So I'm talking about quicksort. The whole algorithm depends on what, guys? The whole algorithm depends on the pivot element that you have seen. To start the process, all n items in the list ls have to be what? In the memory of a what? Single processor. Okay, so let me call that processor name as processor 0. So only then, see, initially we have everything on single processor. Initially we have everything on. See, this is initially on what? Processor 0. Understanding my point, guys? So next to that, look at here. Only then it chooses what pivot and partitions the list. So this initial step is sequentially bottleneck. So you cannot just split the data and start sorting it independently. I can't do that. So another reason is that the division is not guaranteed to be what? Equal. Look at here, guys. So is it dividing both the sides equally? So here we have 1, 2, 3, 4, 5 items. So here we have 1, 2, 3, 4 items. So it is not dividing. See, look at here in this partition. Here we have only one element. Here we have two elements. So we don't have what? Equal distribution, right? So the partition will be always depends on the value of the pivot number actually. Okay. And that can lead to an uneven distributions of work. So that's why I was stressing on the keyword evenly, evenly, evenly. Now here there is no evenly distribution. So where one processor gets a huge chunk of data and another one gets teeny data. So this highlights the limitations of pure data parallel model. So for problems like quicksort, so we need about different kinds of parallelism. So hope this is clear to everyone. Shall I get the confirmation and chat box? So once it is clear to everyone, so please do give me a message and chat box. So is this clear? This quicksort is clear. Yes or no, guys, quickly. Now look at here. So we are exploring this in different example. You can observe here. So the same thing I'm showing you here, guys. So I'm going to give you what more details on this. That's it. Guys, the problem is partitioned at each level of the tree here. So which is a core concept of divide and conquer paradigm. So we have taken step 0. You can observe here. So we start with one processor handling the entire list. So 0 to n minus 1. So entire list is handling by one processor. And after that, we have partitioned data into two parts. So this one and also this one, correct? No. So this will go to one processor. This will go to another processor. How many processors are required here? Two processors are required. Correct? No. And at step 2, each of these two processors picks a new pivot element and partitions its own sublist, creating 4 new subsystems that can be what handled by 4 processors in parallel. Look at here. This is one processor, second processor, third processor, 4 processors. All 4 processors are processing parallelly. So this process continues recursively. So however, there is a what big catch. So as our slide shows, the choice of the pivot M cannot be guaranteed the equal partition. That already I've told you, right? So you might end up with one processor getting a massive sublist and another getting a what teeny one. So this will lead to an unbalanced workload and poor processor utilization. Try to understand this. So it will what go to poor processor utilization. That is very, very important point. So this type of parallelism where the division of the problem is dynamic. Okay, happens during the time of what execution. So this type of problems are called as tree parallelism. So this partitions happen, our distributions happens dynamically. So that's why this is called as tree parallelism. So it is different from data parallelism, what I've explained you in the previous slide. So because of the work is not divided up front, so it is divided recursively as the program runs. Okay, so now let us see, this is the example I've taken here. So this is summarizing everything, guys. This complete slide is summarizing everything, whatever the concept I've explained you. So let's formalize. So we just saw for quicksort, right? The pseudo code here shows how at each step J, you will partition the list and assign the 2 new sublists to the new processor. So it is showing each and every concept by using this code. So this continues until the what sublists are small enough to be what sorted sequentially. So this process is keep on what dividing. See here, we are calling the function partition. So till I get single element, it will be what keep on partitioning. After partitioning, so some of the part is distributing to some processor and some of the task is distributing to another processor. So this step will what continue for all the steps actually. Okay, the performance of this model depends heavily on how good the partition is. Okay, so if you choose a good pivot that creates a what roughly equal subsystems, you can get a what good speed up. Okay, I can't guess like that, guys. Sometime yes. However, with the bad partition, the time taken could be as bad as sequential sort. So this is because one processor might end up with most of the work. Guys, that's why in this what time complexity, we are going to take 3 different types of time complexity, correct? No. One is for best case, another one is for worst case, another one is for average case. So all 3 different kinds of what? Time complexity we can take here. So now you are all understanding, right? What I'm trying to explaining you. Okay, so now you can see here. This is the summary on tree parallelism. Okay, first it is a dynamic version of divide and conquer that already I've told you. And second one is sub problems is identical in structure to the what larger problem. That concept also already I've explained you. So in a quicksort example, each sublist still needs to be what sorted in the same way. And what is the third one? Third one is division or partitions. Partitioning logic is incredibly important. Okay, division is incredibly important here. So for quicksort, the quality of the pivot element directly impacts how balanced the workload is, and therefore the overall performance. Okay, the better you are partitioning, the closer you get to the what equal sub problems actually. The better your what processor utilization. And finally, let's talk about time complexity. Guys, if the problem is divided into k subsystems, okay, here I've given k subsystems. So then the solution can be found in log to the base k n steps actually. This is number of steps we are going to consider here. So with n processor running in a what parallel. So this is very efficient model if you can get good partitions. I told you, in best case, so this is very good algorithm. So the number of processor you have also affects the what outcome. So if you have more processor than you have data items, okay, that is the value of P is greater than N. The value of P is greater than N. So you will have what? Underutilized processors. So which is not efficient. Which is not efficient. If you have fewer processor than data item, that is P is less than N means. So you can get a what? Good utilization. Okay. So that's all about this example, guys. So hope this example is crystal clear to everyone. Shall I get quick confirmation? Shall I get quick confirmation? So now we are exploring a completely different types of parallelism. Okay, that is task parallelism. Shall I jump to task parallelism? Can I get quick confirmation on chat box? Hi, sir. Question here. So how does the ratio of computations to communication overhead change as the tree parallel problem scales up in size? So like the tree becomes larger. Okay. How does the ratio of computations to the communication overhead change as the tree parallel problem scales up in a size? How does it change, guys? Can anyone answer to this question? Yes. So Amdahl's law. So Gafterson's law. So any other answers? Okay. So what is Gafterson's law? Okay. You go back to the what previous session. Then you will understand. So this is one of the what excellent question asked by your friend, right? So this is what gets to the heart of challenges in distributed programming. Am I right or wrong, guys? Guys, as a tree parallel problem scales up in size, the ratio of computation, so the ratio of computation to communication overhead generally decreases. Okay. So in simpler term, as the problem and the number of processor get larger, communication overhead becomes a dominant factor. So how many of them will agree with my point? Yes or no? So what do you mean by computation overhead, guys? So this is the time spent by the processor on actual work, like sorting a sublist or performing a calculation. Correct? No? Are you getting my point, guys? So in a tree parallel model, as the problem is recursively divided, the amount of computations required at each step is reduced. Okay. So see, suppose we have 100 numbers. So we are not performing computations on 100 numbers after partition. Correct now? Equally, we have partition means this side we are going to get 50, this side we are going to get 50. Am I right or wrong? So computations required at each step is reduced here. And the computation time grows, but it is often a factor of the problem size. For an instance, so big O of n into log n for a sequential sort, but the parallel time can be much faster. So for that, what we are going to take log n by p, right? So as we have seen in the previous example, this is about computation. Then what about communication overhead? So this is the time and resources spent on the moving data between processor. So in tree parallelism system, the divide step requires sending data from a parent node to child nodes. And the conquer step requires the children to send a result back to the parent, right? So as the problem scales up, the number of communication steps and the amount of data to transfer can grow. So the core issue here is the communication is often slower than computation. I hope I have answered to the question of Aditya. Aditya, is this clear? Aditya, is this clear? Yes. So any other questions, guys? Sir, you said Amda's law. See, I asked both. Somebody has typed what? One more law, right? So that's why I asked Amda's law. Clear? I did not give answer. Priyanka. Oh, sorry, Priyank. Okay, so now we are moving into the next slide, guys. Look at here, guys. I'm taking one more example. So task parallelism. Now we are talking about task parallelism. Guys, this is another very, very important concept. So till now we have discussed about data parallelism. Now we are talking about task parallelism. Okay, so this is very different from data and tree parallelism because the focus is not on dividing the data. So it is on dividing the task. It is on dividing the functions. Try to understand this. It is completely opposite. Okay, it is completely opposite. So think about a common application you use every day. Okay, so here we have taken the best example, that is word processor. So what are the different functions it performs, guys? What are the different functions it performs? Can you all type on chat box? It handles the user interface for editing. It checks for spelling errors. It saves the document and so on and so forth. Guys, in modern word processor, these functions are handled as parallel task. Okay, so as the slide shows here, so one processor might be running the user interface for editing. Look at here, user interface for editing. While another processor is running spell checker. Okay, so both of these tasks are working on the same data, that is same document you are writing. The data does not need to be what divided here. Guys, this model is great for applications where you have different functionality that can be executed independently. So if you have multi-core system, different threads can access the what same data instance in memory and execute these tasks in parallel. So now you can go to the what core level. So somebody of you were asking about core level, right? So once we have multi-function concept, so then we can go for core concept. So now we are all understanding, guys. So let's look at the what another example here. So let me take one more example to explain on this. That is independent statistics. So this is very much close to data analytics people, right? Okay, so that is called as task parallelism. Look at here, guys. So here, given a list of LS numeric values. Given a list of LS numeric values. So we need to find out mean, median, and mode. So what is the solution, guys? We are using the same type of data here, right? Data is same here, but we are performing three different functions. Okay, means the solution is the task is performing or calculating the mean, median, and mode are all independent of each other. So you can calculate the mean without knowing the median. You can calculate the median without knowing mode. Correct, no? So we can create three separate tasks. So one for each statistics. And run them all time in a parallel. Okay, three functions on same data set. Of course, yes. Yes, that is what I'm trying to explaining you here. Okay, that is what I'm trying to explaining you here. Okay. So the data LS is not partitioned. We are not partitioning any data. The tasks themselves are independent here. So this is a perfect fit for task parallelism. So unlike data parallelism, where the same function is applied to different data. So here different functions are applied to the same data. That you should understand. Okay. So now let us summarize what exactly the task parallelism is. So here I'm summarizing everything, guys. So let's recap the what key characteristic of task parallelism. What is the first one? First one is subtasks are identified based on functionality. And they typically have no common functions. Try to understand this. And this is a major contrast to the what data and tree parallelism. And what is the second subtask? Yes. That is what I'm trying to explaining you all, guys. So that Flint's taxonomy. Okay, this comes under what Flint's taxonomy. Multiple instruction, not multiple data. Multiple instruction, single data here. Okay, multiple instruction, single data. I'm talking about single data. And yes, you can use that in multiple instruction, multiple data also. Okay, so that is distributed computing actually. I can use the same concept in distributed computing. Okay, where the tasks are often identical functions applied to different data sets. Okay, the subtasks are not identified. Subtasks are not identified on the data. So they can all work on the same data instances. Okay, so these independent subtasks are executed in parallel. So this is very crucial point, guys. The number of subtasks is often limited and known statically in advance. This is very, very important point you should understand. So for word processor, you know the tasks are spell checking, right? User interface, right? See, in advance, you know the what function? Yes or no? For statistical analysis, you know you need to find the mean, median, and mode. So this means the parallelism scope is limited and not scalable. Okay, so with more resources in the what same way as data or tree parallelism. So if you have more data, so you cannot simply add more tasks. So however, in a data or tree parallelism, you can potentially get more parallelism by processing more data and making them more scalable with more resources. Okay, guys, this brings us to the what final type of parallelism. So is this clear? Is this clear to everyone? So each and every concept is crystal clear to everyone? Yes or no? So now you're all getting, see, you're all connecting the dots, right? That's why you have to be in patience, guys. So once you are in patience, then definitely you will get answer to each and every questions. Okay. Now request parallelism. Look at the next slide. Okay, so this slide is defines request parallelism as a scalable execution of independent task in parallel. So it explains that each request is serviced in parallel and gives example of system that fit in this model. So like your web servers. Okay. This is one of the final type of parallelism we will discuss, guys. Okay. So can we have 5 minutes break? Hima Bindu, why 5 minutes break? So I have to complete so many concepts. Okay, I will give you break at 7:50, guys. So after that, I'm extending means I will give 10 minutes of break and then I will continue. Is it okay for you all? So today I'm going to show you MapReduce programming. That is very interesting program. Okay, today I will show you MapReduce program. You want me to show programming part, right? So then you have to cooperate today. Okay, I will give you break at 7:50 for 10 minutes and then I'm going to continue. Is this okay for you all? Shall I continue now? Yes, Priyanka, your answer is perfectly correct. See, multiple instruction, single data. So you're performing more functions on single data. SIMD means single instruction, only one instruction you have, but multiple data. That is data parallelism. Okay, so let me complete it, guys. Don't type something in middle. Okay, so I'm in flow. Okay, what is the problem here? What is the problem here? The scalable execution of independent tasks in parallel. Okay, so it is about executing the same code, but in many parallel instances. Okay, that is the problem statement here. Then what is the solution to this? Listen to me carefully now. Guys, this is the model you see in our typical client server application. So when a new request arrives, so it is serviced in parallel with other ongoing tasks that are handling prior request. Correct, no? So each request can be processed by a different thread or different process in the backend. The requests themselves are typically independent of each other. Understanding my point, guys? So for example, when you go to Google, your search query is a request. Okay, your search query is a request. The system processes your request in parallel with millions of other requests from other users around the world, right? Yes or no, guys? Is it not interesting? The core logic for handling the request is the same, but each request is an independent instance of that logic. So this is different from data parallelism. So where you are processing a single huge data sets. So here you are processing many small independent requests. Correct, no? So here I'm explaining you one more concept, guys. System fit in this model. Guys, look at here. Systems that fit this model are those in a what client server context. So like your email servers, okay, HTTP web servers, cloud services with API files and file storage servers. So these are all the what best example for this model. Okay, the key scalability metric for this system is request per unit of time. So that is nothing but throughput. Okay, so request parallelism is about handling high concurrency, not necessarily a single massive computation. Okay, now let's do what quick exercise to see if you have understood the different types of parallelism. So now here we have an exercise for each and everyone. Okay, so what type of parallelism you have to identify now? Okay, guys, let's test your understanding. So based on what we have just learned, so what type of parallelism would you use for these two scenarios that you have to answer? Okay, the very first scenario is historical sales data analysis to find monthly sales aggregates. Yes, now I'm looking for your chat box. What is your answer for the first one? Think about this, guys. It is very easy. Okay, So I got one answer, data parallelism, data parallelism, data parallelism. Okay. Okay. Maximum people are saying it is data parallelism. How we are going to justify it? So you have what massive data sets of sales transactions, right? You need to do the same thing for each month. So you have to aggregate the sales. Does this sound familiar, guys? So this is a perfect example of data parallelism, right? This is a perfect example of data parallelism. You can partition the data by month, send each month's data to what different processor, and have each processor run the what same aggregation code in parallel. This is very common big data use case, and it is what MapReduce was built for. So now we have to understand this is the motivation behind why we have started with MapReduce concept. Okay. Now second one. Can you tell me second one? Web crawler. Web crawler that traverses the web as a graph following links to visit websites to download unique documents. Is it tree? Is it belongs to tree? So this one is bit more complex, right? This one is bit more. See, many of them are saying task, tree. Guys, listen to me. A web crawler starts with a what set of URL, right? So then visit them. So each visited page has links to other pages, correct? No? Because it is hyperlinked. Am I right or wrong, guys? The problem is that the work is not easily partitioned beforehand. So you don't know how many links each page has or where they lead. A new page discovery creates a new task that can be executed in parallel. So this is the example of what, guys? This is the best example of what? This is the best example of tree parallelism. Yes or no? Where the problem is dynamically partitioning, right? So based on the structure of the data. So hope you are all understanding. Is this clear to everyone? I hope this exercise has made the what concept clearer. Yes or no? Okay, guys, now we are moving forward. So what happens in a loosely coupled distributed system? Now purely we are taking distributed concept. Okay, my dear friends, let's now talk about the practical realities of a loosely coupled distributed system. Can monthly sales be task parallelism? Example 2. No, actually, Tanya, you have a what single data set, right? So you have a single data set here. So in this case, you have only single data set. You are dividing your data set as a what? Monthly basis and then pushing it into what different processors. So how come it will become task parallelism? Tanya, you're understanding? If I divide it for product regions, okay, that is depends actually. See, I'm talking about the whole what sales data. So monthly wise, I'm dividing into what different processes. So keeping that mind, I've explained you. That's it. So region wise means again, region wise means you have to divide the data only, right? So divide the data into different processes, right? Tanya. Okay, yes, guys. Now look at here. So everyone look at the slide here. So guys, actually, and now I'm talking about loosely coupled system. Okay, this is the system where the computers are separate and don't share memory. Each and every system. This is purely on MIMD. So you'll be having what? Separate memory. See, you have a what computer system. This computer is having processor as well as memory. I'm going to take one more computer. This will be having processor and separate memory. So all these systems are collected as a what cluster, and this is called as distributed system. Okay, so so one cluster is going to communicate with another cluster by using message passing communication. Okay, here guys, here the setup has huge implications for our divide and conquer strategy. Okay, look at here. First we have taken divide. Guys, the biggest challenge so is that there is no shared memory. So each computer has its own memory and storage. So this means that for any data exchange or coordination between tasks, you must use this message passing communication. So this is the major point of difference from multi-core system on a single machine and multi-processor system. Therefore, when you divide the problem, you must do it in a way that allow the what computation task to run on local data as much as possible to what minimize costly message passing. So you have to keep everything in mind. And next, what about conquer or merge? Guys, the merge phase also becomes more complex. So in shared memory system, it is simpler because each process can just write its result to the shared memory location. In a distributed system, you need to collect data from different nodes. So this node is connected in Bangalore, this node is connected in what Hyderabad, this node is connected in Chennai. See, we are using interconnection network here. Okay, with the help of that, we are collecting the data. The complexity of the merge depends on the problem, guys. So for simple search, so it is low cost merge, just collecting the result. For something like a distributed quicksort, so it is a matter of appending the sorted list. However, sometimes the merge setup, a merge step can become a what sequential bottleneck. For example, in the K-means clustering. So this is the best example. K-means clustering is the best example. In K-means clustering algorithm, you can parallelize the clustering guess, but checking for convergence is the sequential task that requires collecting data from all nodes. Guys, this leads to the perfect, see, this leads us perfectly into the what? Mapper reducer model. So which was designed to handle these challenges. Okay, that's why we have started using what mapper and reducer concept. So is this clear? So this is a kind of what motivation slide I'm giving you to explain mapper and reducer concept, guys. So now we are jumping into mapper and reducer concept. So we have made a what good progress, guys. We have covered top-down design and different types of parallelism. So now we are going to put it all together. Okay, we are going to put it all together. So all these concepts we are going to put in a single concept actually. So that is your map reduce concept. Guys, we are about to what enter the word of map reduce. So you're all ready to enter into map reduce concept, guys. Can I get quick confirmation in chat box? We are entering into the word of map reducing. So this is very interesting concept, guys. Now, guys, you will get the answer for all the questions. So here there is programmers are not going to involve. So only programmer is going to what write the program. That's it. And he is going to upload the data. So remaining all has to be what taken care by somebody else. Okay, that is the beauty of understanding MapReduce concept. Okay, so we will see how this powerful programming model directly maps to the concept of data, concept of tree parallelism we just discussed. Okay, let's do this, guys. Guys, let us start with the introduction part of your MapReduce. Okay, this is very simple but incredibly insightful slide. So it connects everything we have talked about so far to the MapReduce model. So map is all about data parallelism. Look at here. Map is all about data parallelism. Okay, the map phase takes a big problem and divides it into sub-problems based on the data. Try to understand the functionality of map. Okay, it will take the what? Huge problem and divide that huge problem into sub-problems based on the data you have submitted. Okay. So remember our example of keyword search or fingerprint matching. So that's what a map function does. So it applies a simple identical function to each independent piece of data in parallel. This is map actually. Then what about reduce? What about reduce? So reduce is all about inverse tree parallelism. It is inverse tree parallelism. The reduce phase is the conquer part, conquer or combination part of the what problem. You can think of it as a what process where the parallelism reduces with every merge until you get one final result. Okay, the reduce step collects all the intermediate key value pairs generated by the map task and combines them to produce a final smaller output. Depending on the problem, this reduce step may be simpler or even sequential, but it is the core of the consolidation process. So map reduce is a formal programming model that perfectly encapsulates the divide and conquer paradigm for distributed system. The map phase is the divide and the reduce phase is the conquer. That is what you have to understand at the end. So everyone, you're all getting some idea, guys. You're all getting some idea how mapper and reducer is going to work. Yes or no? I want quick confirmation in chat box. I will show you example. I will show you word count example for map reduce later. Yes. Now look at here, guys. I'm showing you the word count program. Okay, look at here, guys. Look at the program. So let us use a what classic example to understand how MapReduce works. So I have taken word count program, guys. So this is the program I've taken to explain you all. Okay, this is the classic example of MapReduce. The goal is simple, guys. Count the occurrences of each word in a set of documents. Understanding my point, guys? So let's look at map function. So where is your map function? So this is your map function. Okay, the system feeds this function a key value pair. So it will entering what key value pair for each and every data available on your system. Okay, so in our case, key would be the what document name. Key would be the what document name and value would be the text of document. Okay. So what does our map function do, guys? It iterates through every word. It iterates through every word in the document text, and for each word, it will emit a new key value pair. Okay. The new key is the word itself. Look at here. You can see here. The blue ship on a blue sea. So here, this is one word. This word is emitted with value 1. Okay, for the entire document, it will do the same thing. Next, it will take the second word. So it will assign value 1. Next, it will take the next word. It will assign value 1. Next one, next one. So like this, the mapper is going to what? Divide the entire text document into words. And it is going to emit with key value pair. So key would be the word and the value would be the 1. So this is the what? Divide phase, right? So what it does, guys, it has taken the entire document and divided into what? Different parts here. And it is making a pair. So each map task words on a separate document independently what creating a list of these intermediate key value pairs, and all these pairs are then sent to the next stage. Is this clear to everyone? Yes or no? This I will explain later. This I will explain later. See here what it is doing. It is collecting blue and it is consolidating value 1, 1. So how many on we have here? We have only one on. So it is taking here. How many C we have here? So we have only one C. It is taking one value. Suppose we have more than one means, so it will take both the values. So this I will explain later. So have you all understood map function? Mapper function is clear to everyone. Shall I get quick confirmation in chat box? I don't want to compromise myself, guys. I want each and everyone to understand this because this is very, very important for your examination. Okay. So next, let us see what happens with respect to reduce. Guys, this diagram beautifully illustrates the word. See, look at here, guys. Reduce means, so it will shuffle the data. So this is called as shuffling. So we have a separate functions to shuffle the data and we have a separate functions to sort the data. So after mapper function, we have to call these two functions, shuffle function and also sort function. Our mapper and reducer functions you are calling means by default, Hadoop will perform the what shuffle and sorting. So no need to separately, we have to do it. Manually you're doing this, then you have to do separately. Okay. See, after this, see 1 is adding and it is becoming 2 here. And on 1, C1, shift 1 and da 1. The meaning of this is, so we have performed addition operation. After performing addition operation, so we have conquered all the data. We have conquered all the data. That is the job of reducer. That is the job of reducers. Okay, so let me show you with the diagram, guys. Let me show you with the diagram. So once again, guys, so you all look at here. I will show you very beautiful example to understand this. So look at the example showing here. See, so how it is splitting data. See, this is one processor, this is one processor, this is another processor. And what mapping is doing? So mapping is dividing each word into what? So each text, see, this is the text, right? So it is dividing into word and assigning with one. And shuffling is collecting the data. And reducing is counting the data. And finally, we are performing conquering operation. So this animation is crystal clear to everyone. Now you all understood, right? What is the function of map? What is the function of reducer? So now we are all getting clear idea, guys. I want each and everyone to respond now. Sir, one more question. One more time, please. Yes, I will show you one more time. Okay, this is what exactly. Okay, look at here, guys. This is one complete document. Okay, I will show you here. So this is the animation. Guys, this is the complete document I've taken here. See, this is the input. So input is nothing but what? One complete document. This document is splitted here among what? Different processors. Okay. And after that, we have called mapper function. So mapper function is dividing this complete text into different words. And each word is emitted with one value 1. Look at here. Welcome 1, 2, 1, Hadoop 1. Same with respect to second one also. See, parallel. So because we have distributed data among different systems. We have distributed data among different systems. So why no voice? You're not getting my voice, guys. Is my voice clear to everyone? Am I muted? No, right? Screen gone. Guys, tell me whether it is earlier it was not okay, regained. So now my voice is clear. My voice is clear. So everything is paka, right? Okay, fine. Okay, fine. So come back to here, guys. See here, as I told, so what it is doing? So it is taken some input data and splitted input data to different processors. So inside this processor, it is calling mapper function. So mapper function is going to perform the task. So that emit task, and it will create a what key value pair here. And then we are performing shuffling and sorting here. Guys, this is a crucial hidden step. Okay. So the framework automatically shuffles and sort all the intermediate key value pairs. So it groups together all the pairs with the same key. Same key. So all the blue comma 1, look at here. All the, see, in previous example, we have taken blue comma 1, right? All blue comma 1 will comes to one place. Okay. And next, see, next to do that, so we have a reducer concept. So reducer receives the word. Screen is not shared up. Sir, it is visible. Then what is the problem? Saini, can you check from your end? It is visible, right? Saini, can you log out and log in? Okay, so what reducer is going to do? The reducer receives a word and a list of all its count. Okay, the reducer then sums up all the one in that list to get a what final count for the word. See, for example, the reducer for the key blue. So in previous example, so we would have got what 1 comma 1 here. So 1 comma 1 means we have to add these two values. After adding these two values, I'm going to get 2 here. And look at here, guys, the final outcome is conquered back. So the reducer emits the final key value pair like what? Bad equals to 1, a bad 1, class 1, good 1, Hadoop 3. So everything. So which is then returned to the what final output file. Guys, the entire process from splitting the input to getting the final outcome is managed by MapReduce framework. So all you had to do, see, all you had to do was write the simple logic for map, write the simple logic for reduce function, and then try to execute it. So, okay. So mapping is done, allocated processor, but so where is shuffling is happening? See, this is completely happening in one system. This is complete. See, guys, so once you have installed Hadoop framework, okay, once you have installed Hadoop framework, so these two are hidden part actually. Sorting and shuffling is a hidden part. So this has to be what taken care by Hadoop framework. Okay, in word count 2 diagram during mapper, where exactly the partitioning is happening, sir? Where exactly see here what we are doing? This is the entire document. So this partition we are doing, right? So we are distributing data to what different processes, right? So this is partition actually. Is this clear? Arup? Sir, is the final output is also key value pair? Yes, it is also key value pair. But it is going to show, see, according to word count, so it will show the number of word present in the document. So it is also kind of key value pair. Okay. Or you can see for examples, guys, suppose you are downloading data in what? CSV format means the output would be always there in a CSV format. So this could be the what last format actually. No, better you should not consider it as a key value pair. So this is not purely key value pair. Sir, I have a question. What will happen in case of case 1? So why to use Hadoop? I will tell you, you have to wait for one more session. You have to wait. See the entire, see why we have introduced big data system. So why we have introduced big data system? That is to learn why to use Hadoop. Okay, so you will understand why you people have to use Hadoop. So many of them are saying, right, I'm not good at programming. So those who are not good at programming, then no need to write mapper and reducer code. So everything is available in a Hadoop framework. See, we are teaching you what? A to Z. But at the end, after learning all this Hadoop framework, no need to learn any programming language. So only you should know how to handle the Hadoop ecosystem. That's it. That is the beauty of learning big data tools. Hadoop is good. How will it treat Hadoop? I will tell you. Okay, I will tell you. See, Varun, you have to wait for a while. So next class, I'm going to explain you everything on Hadoop system, Hadoop ecosystem. So there you will get fantastic idea. Shall I proceed, guys? Guys, it is already 1:27, so 7:27. Now look at here, guys. So again, I'm prolonging here. This is the mapper step I've given separately. The map function which you provide is executed on a set of input key value pair. The input could be something like document ID, document content. So here it is clearly mentioned. The map function takes a single key value pair, so which is mentioned as k comma v. Okay, and processes it. The output is list of intermediate key value pair. So k1 v1, k2 v2, so on, kn vn. Okay, the important thing is that the intermediate key and value can be different type than input key and value. So for our word count example, the input was document name and document text we have taken. Okay, the output was word comma 1. Okay, the beauty of this is that the framework handles the rest. Already I've told you, right? It takes all the intermediate key value pairs from all the map task and prepares them for the what next stage. That is the beauty of using Hadoop ecosystem. Okay, that is the job of mapper and reducer programming. So now let's see how to reduce the steps takes this turn. This is mapper function. This is reducer function. Okay, reducer function I'm explaining you here. So after mapper phase, the framework automatically groups all the intermediate key value pairs with the what same key. So the reduce function does not receive a single key value pair. It receives a single key and a list of all the values associated with that particular key. So this is very similar to SQL group by operation, guys. Okay, for our word count example, the reduce function for the key blue. So we have taken the example of blue, right? So would receive blue and the list of values. See, it was showing in bracket, right? 1 comma 1 comma 1 like this. So the list of values and also word we have received. What is the word? The word was blue actually. This is the pair we have taken at the end, right? The reduce function then processes this group to procedure a final output. So which is a key value pair again. Okay, so that is key. See, look at here, key value pair again. So after reduce, so we are going to get again key value pair. So this is like a SQL aggregation function. The programmer's job is simply to write the logic for mapper and reducer function. The framework handles all the complex work of distributing the data, running the task, shuffling, sorting, and handling failures. Is it not interesting, guys? So if it is interesting, can you all put a message on chat box interesting? If it is interesting, can you all put a message on chat box interesting? This is the formal definition of mapper and reducer. This is the formal example of mapper and reducer. Look at here, guys, everyone. So here we have input. The input is a what set of key value pair. Okay, and the user supplies two functions. One is mapper function, another one is reducer function. Okay, and yes, so user. Okay, user supplied function. The programmer must provide two functions here. So one is mapper function, another one is reducer function. Okay, so what mapper function will do, guys? The mapper function will take the input key value k and value v and produces a list of intermediate key value pair. And what reducer will do? This function takes the intermediate key k1 and a list of v1 associated with the what key value, and it produces a final value v2. Correct? No? Then what is the output here? So output is a set of k1 comma v2. So v2 is the final result here. So this diagram will give you the what? The entire concept of key mapper and reducer concept. Guys, can you all tell me when you will use this? Can anyone answer? So when you are going to use this function? That is the next question I'm asking you all, guys. When will you use this? When would you use this powerful but restricted model? Not see, don't don't give me the answer like aggregating data, guys. Any functionality I can do, guys. So when we want to apply a same type operations on a set of data and collect the result at the end. Okay, very brilliant answer. Guys, you would use it when you have a huge set of document that don't fit into memory. Guys, your complete Hadoop ecosystem is a distributed system. So once you don't have enough number of memory, then you can use this Hadoop system. So this is the classic big data problem, MapReduce, especially with the system like Hadoop. So this is designed for this exact scenario. So it performs file-based processing in stages. So each mapper task processes a file chunk and writes its immediate result to the local file. Then the reducer task read those files to produce the final outcome. However, so you can also use this model for in-memory processing. Okay, you can use this model for in-memory processing. For example, with a system like Spark. Spark uses a structure called RDD to keep data in memory. So which is much faster. MapReduce is ideal for problems that have a lot of what data partitioning and possibly simple merge among what partitions. Guys, the model shines when the problem can be broken down into independent subproblems that can be solved in parallel. So in that situation, so we are going to use this mapper and reducer concept. So everything I explained you over there. And this is the mapper and reducer execution overview, guys. You just look at here. So I'm giving you one more diagram here. You can observe. So we have a user program. You all can observe here, guys. So we have a user program which you write starts the process. It first forks or initiate the master process. Okay, look at here. So this is your user program. I'm going to start from here. So it will fork master function. Listen to me carefully. This is very, very important. Okay, these steps are very, very important. So user program. So we have a user program A, and it first forks or initiate the master process. Okay, so initially master process is called. What is this master? The master is the brain of the operation. So it is responsible for managing the entire job. So somebody asked, right? So who is going to perform scheduling? That is done by master program. So who is going to send data to particular system? That job is done by this master system. Okay, so it takes the input file from the distributed file system. So it will, so from where it is going to take? So it will take the data from the HDFS that I will show you later. Okay, and divides the entire data into smaller chunks. That is the job of master node. And next to master node, we have a mapper function. Okay, next to master node, see here, we have a mapper function. Look at here, assign map. See, we have assigned a map here. Guys, the master then assign map task to available workers. See how many workers are available here. So worker 1 is available, worker 2 is available, worker 3 is available, worker 4 is available, worker 5 is available. The meaning of this is, so workers are nothing but different computers in a cluster. Or workers are nothing but different computers in a different cluster. So each worker processes its assigned chunk of input data and produces intermediate result. So which are returned to a what? Local disk or intermediate file. Understanding my point, guys? So this will push back to the what? Intermediate files. Understanding my point? So till here everything is clear. This is the job of master. Master will assign mapper function. So worker is equal to data node, master is equal to name node. Perfectly correct, Anu. Okay, so your answer is perfectly correct. That I will explain you later. Now, theoretically, you understand everything. Later on, I will give you the exact terminologies. But your answer is perfectly correct. Okay, so now look at here, guys. Next, we have reduce phase. See, look at here. Who is assigning reducer? So once all the map tasks are complete, see, this worker is going to send an information to the master. I've done with my job. This is also. So here we are going to call it as heartbeat. So we will receive heartbeat from master to worker, worker to master. So this is going to acknowledge. So I've done with my work. So once the work is done by mappers, the master assigns reduce task to other workers actually. So other workers, again, workers are behaving like what reducers here. Understanding my point, guys? So those who have completed the job, that will be what behaving like a workers here. So these workers read this intermediate data. Read this intermediate data from the map workers and sort and group the data. So this is performing sorting. This is performing shuffling. This is performing the what? Running the what? Reduce functions on it. And finally, we have an output here, right? So the final output is returned back to the distributed file system. Okay, you just imagine, guys, this is a U system. Okay, this is a U system. Suppose I need 2 file system to store output means, so it will distribute data among 2 output system. So once the data size is huge, so I can get data in a what? Output in our different files. That is also possible. Again, this output is distributed. Later on, we can get what? Each and everything. That I will show you in real time. Okay, so this is the key concept behind mapper and reducer concept. So if you have any doubt, please do ask me, guys. Guys, the key takeaway is that everything is handled by the framework. So framework handles everything. So it is a data-centric design, guys, where the computation is moved closer to the data to minimize the network traffic. Okay, the framework manages resource allocation, task scheduling, data movement, and most importantly, fault tolerance. Okay, so if a worker fails, the master can simply reassign its task to another worker. So this is a powerful concept that abstracts away all the complexity of distributed computing. So now tell me, guys, is it interesting concept? Is it interesting concept? In case 1, Hadoop has question mark. And in case 2, Hadoop does not have question mark. So how will mapper and reducer treat it? So do we need to clean data for special characters? So that is depends on you, Varun, actually. So you're considering question mark as a separate word. Tell me, you want me to count the number of what special characters? That also I can do, right? So once it is yes, I'm going to consider question mark as a what separate character. I'm going to count the number of question mark also. Number of exclamatory mark also. Guys, can you all tell me how we are going to differentiate words? How we are going to differentiate word? In CSV format, you are going to differentiate word by using comma operator. Okay, in normal text format, you are going to differentiate by using space, single space or multiple spaces. Correct, no? In tabular column format, you are going to separate by using tabular what space actually. So that is depends, guys. So is this clear to everyone? Suppose see, as your friend asked me, why immediately I have a question mark means this completely considered as a single word. Okay. Suppose we have y space question mark means, so based on my mapper function, this is a separate word and this is another separate word. Varun, is this clear? So till here everything is clear, guys. Guys, that in the diagram we can see only one master and many worker nodes. That means in one cluster only one master node. That I will show you later. Okay, that I will show you later. Arup, can you wait for a while? Can you wait for a while? So for a time being, you understand we have only one master now. Okay. So very interesting question. I will show you later. So this is MapReduce origin. I don't want to explain you the history of MapReduce, guys. So this you can learn by yourself. Okay. So next, guys, look at here. So next we are going down and we are looking at what MapReduce program works using Hadoop. So can I show this program after 10 minutes break, guys? Can I show this entire program after 5 minutes break or 10 minutes break? How much break you want, guys? Okay, 10 minutes. 10 minutes, 10 minutes. Okay. Okay, guys. Now the time is 7:43. So I will come back at 7:53. Okay, sharp 7:53. I'm going to start the class. So do we have extended class today? Yes, yes, Pradeep. Because you only know, right? Many people are asking many questions. So in between, because of that reason, last class I have not taken any questions. Okay. So this time I have to see here, I have to answer all the questions and then I have to complete the syllabus. So since it is very important concept, I don't want to compromise. So that's why I'm extending the class, guys. So I need your cooperations, guys. That's all. I can't say anything else. Okay, guys, after 10 minutes, we'll continue. Is it okay? What if master node fails, sir? Everything I will explain you. So Upadhyay, you're feeling very interesting, right? So you're feeling very interesting, right? So I will explain you each and everything later. No need to worry. Okay. So in Hadoop class, next coming class, I'm going to explain you each and everything. So it is must you have to attend what? Sixth session. So in sixth session, you're going to get answer for all the questions. Okay, that I'm taking on next Saturday. So Saturday I'm taking sixth session. Sunday I'm taking seventh session. Clear, guys? Fine. Okay, guys. After 10 minutes, we will meet. Yes, guys. So I'm back. What about you all, guys? You all back? So once you all back, please type me message and chat box, guys. Back. So quickly, I will start with the session. Guys, don't ask me any questions on how to write a program. So program and all, I will explain you in the lab session. Okay. So today I'm going to show you how to execute this program. That's it. So each and every concept I'm going to explain in the lab session. Okay. So is this clear? And see, I'm going to post you both mapper and reducer program, guys. So on chat, on what discussion forum, or I will post you guys somehow I will post you. You just go through the mapper and reducer program. Okay. So later on, I will explain you each and everything. So in detail, when I'm going to teach you the lab session. So is it okay for you all, guys? Is it okay for you all? Yes. See, before I'm going to perform this, so I'm going to show you the data set, guys. So somewhere I've downloaded data set. I will show you the data set. So one second, it is there in, yeah, here. So this is the data set I have taken. So all of them, look at here, guys. So we have transaction date, product, price, product type, name. So name of the what? State, I think. No, this is name of the person, city name, state, country, and then we have account detail, account created, last login date, and latitude and longitude. See, all these informations we have in this file. And this is CSV data files, guys. So this is CSV data files. So it is giving sales data processing. So I have taken sales data of January 2009. Okay. So I have taken January 2009 data set. That's all. So as I told, it is containing so many values. So is this clear, guys? This is about your data set. So now we are getting clear idea on data set. What exactly it is? Yes. So now, guys, imagine you have a what huge data set of sales transactions. So maybe what spanning years, and it is too big to fit on a what single computer. So as you can see from the what spreadsheet shown you, the data has a what lot of columns and also including what transaction data, sorry, transaction date, price, country, so on and so forth, right? So here our goal is to count the number of transactions by country. So is this problem statement clear to all, guys? So is this problem statement clear to all? So we have to count the number of transactions by country. That is the problem statement. Okay. So this is a what perfect MapReduce problem, because so it is a what massive aggregation task that can be easily parallelized. Okay, I will show you the number of columns also, guys. See here, I'm clicking on this. So look at here, guys. I have 999 rows here. I have 999 rows. Or you can take more than that also. You copy and paste the same. So you'll get what 2000, nearly 2000 data. Understanding my point, guys? So country wise, I'm calculating what? Country wise, I'm counting the number of transactions. That's it. So hope you are all understanding. Yes or no? So this can be achieved by using mapper and reducer program. Okay. So look at the screenshot here. So I have shared screenshot, right? So look at the screenshot. So I have taken the same data set. Okay, let me write here. I've taken the same data set, and this is what the output I'm expecting. So Argentina 1, Australia 38, Austria 7, like this. So finally I have to calculate, count, see number of transactions. with respect to all these countries. So hope this is clear to everyone. Yes or no? Is this clear to everyone? So this is the input and this is the output I'm expecting. Okay, now look at here, guys. So this and all I will show you later. See, the very first command, we are using ls minus l. Okay, I will show you here. Guys, actually, I have installed mapper and reducer on my system. Okay, I have installed mapper and reducer on my system. So based on that, I'm showing you each and every result, guys. So this installation, suppose you have to do by yourself, means you can do by yourself. Otherwise, you can use the lab what we have provided. So my suggestion is always to experience the complete architecture. You have to install by your own on your computer. Okay, I have installed on WSL, Windows Operating System. Suppose you have a Ubuntu operating system, then it is very easy to install, guys. Okay, so now what I'm going to do, say I'm showing you what and all files are there here. Okay, let me show you what and all files are there here. So by clicking ls, so it is going to show, see the data set is ready here. Sales Jan 2009. See, this is the data set I have copied, and this is the function name I've taken, sales mapper.py, and this is reducer function I have written here. So this is our Hadoop, and this is my own folder or directory. This is word count program mapper.py, and this is reducer.py. This is another word count program. This I will explain to you later. And one more text data I've taken as test.txt. I have one CSV file and I have one what test.txt file. Okay, so this is the what data I'm showing you all, guys. So here you can observe. So here they are having what all these data values. Okay, so sales count driver. Don't worry about what and all data they have taken. And I have written everything by using Python code. So here they have written everything by using Java code. Okay, you can write the program by using Java, or you can write the program by using Python also. Guys, mainly Hadoop is written by using Java programming. So that's why we have so many jar files here. So Java jar files, by using that, they are what? Writing mapper and reducer codes, guys. So I'm not writing mapper and reducer code by using Java. I'm writing mapper and reducer code by using Python. So do we have document for installation of mapper and reducer? No need to install in mapper and reducer. So once you're installing Hadoop, that is more enough. So once you're installing Hadoop, that is more enough. See in Hadoop, what mapper and reducer is default. Okay, that I will show you in the next class. Okay, that I will show you in the next class. Next class I'm covering on, sir, can you share Python code also? Definitely I will share you guys. No need to worry. I'm going to share you everything. Okay, and see this step is clear, right? So whatever the program we have stored, everything it is listing here. ls minus l you are giving me, it will show in detail. That's it. So let me show you. These are all commands by what? Linux. So once you are familiar with Linux, then these are all same. The same thing it is showing here. Okay. So hope this is till here everything is clear. Till here everything is clear. Okay, so look at here, guys. I'm going to show you both the programs. Okay, so and next to this, see here, we have a what JPS command. So JPS means Java Virtual Process Status. Okay, or Java Process Status. Okay, Java Virtual Machine Process Status, we can call it as. See, once I'm clicking on JPS, so it will show secondary name node, resource manager, node manager, JPS, data node, and map master and name node. So this is not required. Map master is not required. Okay, so what and all required to run our code? Name node is important for us. Data node is important for us. Node manager is important. Resource manager is important. Secondary name node is also important. So one of my friend was asking this question, right? So sir, do we have any alternate master node? So we have alternate master node here. So one is node manager, another one is secondary name node. So this secondary name node is a backup for this name node. So somebody is asked, right? suppose this file corrupted means, so it will take the backup from resource, secondary name node. That I will explain you later, guys. So I'm going to show you the practical thing. That's it. So I'm typing JPS now. So once I'm typing JPS, so it will list all the daemons. We are going to name it as daemons. Okay, so daemons is nothing but the means what? The programs running behind or background. That is called as daemons. DAEMON. Daemons. So it is listed all the daemons. Sir, one clarity needed. Map reduce concept are clear, but I am trying to align this with real world example that when the reducer process the data, show the total counts, how this data can be meaningful. Sorry for asking silly question. Yes, no need to worry, Ravi Kumar. Ravi Kumar, you just imagine. So now we have to what? Calculate number of words in a given document. So that is the task I have given to you. Okay, otherwise I have shown you, right? So now I have shown you, right? So country wise, I need what? Number of what? Transactions. Otherwise, date wise, I want number of transaction. Then map reducer is helpful, right? Yes or no, Ravi Kumar? Ravi Kumar, you are understanding? Okay, yes, guys. Now look at here. So look at here, everyone. So next to that, I have checked with this. I've checked with this. And one more question you can ask me, guys. So how you are going to start all these daemons? That question you can ask me, right? So now look at here, everyone. So better you note down all these commands, guys. Commands are very, very important. Guys, so we have a command here, start yarn.sh. So we have a command, start dfs.sh. And we have one more command, that is stop all sh. I will show you. Suppose you are typing stop hyphen all dot sh. So it is a script file. Stop all daemons. The meaning of this is stop all daemons. So once I'm entering this command and pressing enter, so it will close all the daemons running in the background. Okay, so it will take some time, guys. You just look at here. See, you look at one by one. See, it is stopping name node. It is stopping data node. So it is stopping secondary name node. Yes, it is all the part of Hadoop installation. So next is node manager. It is closing. See, everything is stopped. So next I'm typing JPS. So once I'm typing JPS now, so it is going to show only JPS. See, all the daemons running on background is stopped. Understanding my point, guys? So hope you are all understanding. Yes, it should be inside. Yeah, exactly. That and all details I will give you later, guys. You just understand what I'm explaining you all. So this command is very, very important. Stop all sh is very, very important. Now I have to start all the sh. So start hyphen all dot sh. See, this will start all the daemons. Okay, this will start all the daemons. See, once you have pressed enter, so automatically it will start all the daemons on the system. Okay, on your Hadoop system. So look at one by one. Starting name node, starting data node, starting secondary name node. Okay, starting secondary name node. And then yes, starting resource manager, starting node manager. Okay, so everything is done, guys. Now you click on JPS. So it will list all the daemons. So is this clear? So only one time we have to perform the installation, guys. So automatically it will install all. So what are all the numbers when we run JPS command? That is port number. That is port number. Or yes, it is not port number. Sometimes yes, we can call it as ID also. It is not port number, it is ID. Okay. Is this clear? Is this clear to each and everyone? Till here, everything is clear, guys. Okay, now look at here. Now look at here. So everyone, Control L you are pressing means, so it will clear the screen. Control L will clear the screen. Now guys, now I have this. Okay, let me show you the data. So where is the data? So once again guys, Control C, Control L. Yes, ls minus L. So this will list all the files. So now very first thing what I have to do guys, suppose I will show you some concept now. Listen to me carefully. Guys, before you run this mapper and reducer code, you have to upload. So you have to upload input file to HDFS. Okay, input file to HDFS. Remember this. So before you are going to perform this task, you have to upload input file to HDFS. So what is my input file here? What is my input file here? What is my input file here, guys? That is CSV file, sales, Jan 2009. That is my input file, right? So how we are going to upload the file? So to upload that file, I'm going to use the command. See, I'm uploading it into HDFS. So HDFS, and then I'm typing DFS. Next class, I'm going to explain you each and every commands, guys. So minus put. So put is the command used to upload data to what? Data to what, guys? Data to your HDFS. Okay, before that I should know, right? So where exactly this file is stored? This file is stored in home / what Hadoop user. This is the folder name we have to copy, right? This is the folder name we have to copy, right? So next to that, now what I'm going to do, I'm going to type HDFS DFS hyphen put. So this will what? Upload the file to. So which file it has to upload? It has to upload. Let me copy this and I'm pasting this here. And what is the name of the file, guys? Name of the file is sales something, right? So once you're clicking on this, automatically it will copy. Once you're pressing tab, it will take data automatically. Okay, home, Hadoop user, sales Jan 2009.csv is the file name. See, I've taken the path here. So after that, where I have to upload this, guys? I have to upload this to root. So what is the command for root? / right? So this will upload the what? The sales Jan 2009 data to root of your HDFS. So is this clear? No, post and all we are not going to use here. We are going to use put. We are going to use one more command. We can copy from local to what? Another one. You just take the snapshot of this, guys. Okay, otherwise I will share you code. Each and everything I will share you later. Okay, just look at here. So now HDFS, DFS. So before this, guys, before this, I will show you one more thing. So everyone look at here. So I'm going to show you one more thing. So let me see what is the user interface. Okay, once again, guys. See, to see the user interface, so we have to click on the C. This is localhost 9870 you are giving means it will redirect to Hadoop UI. Okay, so now inside Hadoop UI, you just look at here, guys. So you click on utilities and then browse the file system. So inside file system, do you have that file name, guys? Look at it. Do you have that file? You have own, you have sales, you have TMP, you have user, you have word count. So do you have that particular what sales Jan 2009 year? No, right? So now look at here, guys. I am uploading the data. After uploading, see, I'm pressing enter now. So once I'm pressing enter, the data is uploaded successfully. Okay, the data is uploaded successfully. Now I'm going to view the data. So now I'm going to refresh this, guys. So once I'm refreshing this, see, look at here, guys. The data is uploaded on HDFS. The data is uploaded on HDFS. See, previously I had only this much. So now this file is uploaded on your HDFS. This is the content of your HDFS. So hope this is clear to everyone. Yes or no, guys? Yes or no? Till here everything is clear. Till here everything is clear. Okay. Sir, one doubt. So once we start the Hadoop nodes, so will it open a SSH session? Yeah, yes, of course, yes, sir. So to perform communication, SSH is very, very important. Guys, before starting my class, I have what? Encountered SSH problem. So I have taken what? 2 hours to what? Clear that problem, SSH problem. Okay, SSH is very, very important. So that is going to play the what vital role in Hadoop installation. Clear? For communication, we are going to use that. So shall I proceed now? Shall I proceed now? So now, guys, your file is ready. Now what I have to do? I have to run my mapper and reducer code. Okay, to run mapper and reducer code, guys. So I have to type one big command. So everyone look at here. I will show you that big command. I don't know where I've typed that command. Somewhere I've typed that command. So once it is not present, then I have to type the entire command. It will take lots and lot of time to type this. Okay, it is not present here. Okay, it is not present here. Okay, I'll do one thing. So I will type the command, guys. You all note down this. So this is another very, very important command. What I can do is, so let me check here. So maybe I have used long back. See, guys, how many commands I have tried here. Since morning, I'm installing the software. So installation done successfully. Yes, this is the command we are going to use, guys. So can you all look at here? Can you all look at here? Everyone. See, all of them look at here, guys. This is the command I'm typing on this. I'm going to paste this on your chat box. I will explain you one by one what it is. Okay, I will explain you one by one. So now listen to me carefully. Okay, I will do one thing. I will paste this on new slide. I will increase the font. This is very, very important command, guys. And this is unique command. So I will tell you what and all you have to change now. So this is the previous one I've taken. Now I will show you. Let me increase the font. Yes. Okay. Now look at here, guys. Okay, I'll do one thing. I will take, okay, this is not bullet. Let me remove the bullet. So let me split this into different parts. So I'm taking files, and then I'm taking mapper function, and then I'm taking reducer function, and then I'm taking input, and then I'm taking output. So this is the file system I've taken, guys. Look at here, everyone. Okay. So all of them listen to me now. See, initially I have taken the command Hadoop. I have told you, right? The entire program is written by using Java. Okay, the entire program is written by using Java. So that's why what we have to do. So we have to include this Hadoop streaming 3.3.6 jar file. So this jar file is present on this what location. So I've taken the complete path of this jar file because we have written the entire code in Java. So now I'm writing code in Python. So without this, I can't execute my program. So this is mandatory. So that's why first we have to write Hadoop and then jar file I'm running. So what jar file? This jar file I'm running here. Okay. So this you will get to know at the time of installation. So that's why I told you to go with installation by yourself. And next line, look at here, guys. What and all files I've taken? I've taken two files. So one is this is ./mapper.py, comma ./reducer.py. Why I've taken /? Can anyone tell me? Why I've taken /? What is the reason? So what do you mean by /? Means? / means what? No, this is not current directory. No, slash means current directory. I've taken / here. I've taken /, right? That is not a path, guys. This is the executable file. See in what C programming. So once you are using C means, then what you are going to get? A.out ./a.out you are going to get, right? So this is the executable file actually. So Python, see here I'm executing the file. So the same executable file I've taken here. ./mapper.py. So order is not important here, guys. So any order you can maintain. So first you can write mapper, reducer, input, output, and later you can write files also. So order is not mandatory. So in Python environment. Okay, so this I've taken here. I've taken two files. One is mapper function, other is reducer function. And what is that mapper function? See, this is the command I'm using to execute mapper file. This is the command I'm going to use to what? Run my reducer code. And this is the input I'm taking. So I'm taking input directly, right? This input I'm not taking there. So something else I'm taking, but here last program I've taken here. And this is the place I'm going to store the output. So this is input path. This is input path. And this is output where I'm going to store output at the end. So this is output path. So is this clear now? The complete command is clear to everyone? Yes or no? Complete command is clear to everyone? Yes. Now quickly, guys. So quickly I'm going to do some changes. According to my program, I'm going to do some changes. So where I'm going to store the output. So 1 second, guys. Oh, sorry, guys. By mistake, I've typed. Okay, where I'm going to store the output, I have to mention the output folder name here. So let me write output folder name as out123. This is the folder name I've taken, guys. Otherwise, let me do one thing. Let me write it as mp out. Okay, mr out. Okay, map reduce output. So I've created one folder. So this is where it is going to store the result. And next, from where I'm taking the file name. What is the file name I'm taking here? So directly I'm taking the file name, right? What is the file name? Sales. Okay, that is sales. 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 Okay, here somewhere I have right. I will copy this file name directly. Control C. And then I'm pasting here. So this is the input file I'm pasting. So sometime it will demand for path also, that I will check later. So if it is yes, better we can take slash here. So why slash? Because this is inside the root, right? So that's why I'm taking sales Jan 2009. This is my input file. And what is the program name I'm taking? See, I'm program name. This is for sales mapper and sales reducer I'm taking here. Correct? No. So I'm going to take this as a sales mapper. Sales mapper and sales reducer. I'm changing according to my program name. Sales mapper and sales and where we have taken one more time. So here we have taken right. This is sales mapper and this is sales reducer. Okay. So hope till here everything is clear. So let me write this command on your chat box. This is the modified command. Okay, this is the modified command, guys. Suppose you are taking the same file name as this is the command you are going to use. So is this clear to everyone? Is this clear to everyone? Till here everything is clear. Shall I click on enter button? Shall I click on enter button? So let us see the magic. Guys, many of them are worrying, right? So I have written program in mapper, I have written program in reducer, I've taken input file and I'm entering this command. That's all. So now guys, no need to worry about mapper concept. No need to worry about sales concept. At the end, I'm going to get the output on the screen. So do you want to see that change, guys? Do you want to see that magic? Yes or no? Yes. Now look at here, guys, everyone. Look at the program. I'm pressing enter. So once I'm pressing enter, so it has started distributing data. So look at the code. Look at the code it is running. So it is creating log file. It is running mapper code. It is running reducer code. I will show you this later. So you keep on observe here. See, look at here. Mapper is completed 0%. Reducer is completed 0%. Now it is running in background. So mapper completed 100%. So now the task of what reducer. So reducer is completed 100%. And finally, I got the output. So where it is stored output, guys, output directory /mr out. Correct, no? /mr out. So now let me see whether this file is present here or not. Where is this? Yeah, here, right? So I'm refreshing this. See, look at here, guys. It is created a new folder name. The folder name is mr out. And I'm clicking on this. So once I'm clicking on this, it is going to show two files. So once it is successful execution, then it is going to show success. And this is where our output is stored. Part 00000. So guys, this is the default name of your output file. And you have to look at here. What is the size of this memory? So this block size is 128 MB. This I will explain you later. So in next coming class, I'm going to explain you in detail. So how we are going to fix the block size. Okay. So where we have stored output, guys. So where we have stored output. And you can see node manager status also, guys. Okay. This is going to show node manager status also. Look at here. So this is the complete task distribution. See here, mapper and reducer code is running. See on 31st August. Okay, finished, succeeded. See, all the informations are stored here. Okay, this is window also I'm going to show you next. See, you once you're clicking on notes, so it will show all the notes. See, it will show all the notes. So my node name is desktop J6KCU OA. Okay, so node labels, everything it will show, guys, that you can experience later. Okay, so now shall we see what is there inside the MR out? So what is there inside the MR out? Then what we have to do, guys? So it is stored on ls minus L. Where is minus? Okay. Here. Look at here, guys. Ma out is created, right? So where it is created, ma out. Inside part. No. That part is different. That we had previously, right? The same thing it is showing. It has to show the folder name, right? Why it is not showing folder name? Is it directly stored on? It's directly stored here, right? But it is showing 0 bytes. So why it is showing 0 bytes? Okay, so inside that we have data. Let me show from here. So let me download this file. So it is not allowing me to download. There is an issue, guys. That's why it is not downloading. Even it is showing some error here. So this I have to encounter, guys. It has to show the file name, but it is not showing here. Not an issue. I will do one thing. I will try to download from here. MR out, right? The folder name is MR out. So let me download this file from here. So to download files from here, I have to type again HDFS DFS -get. So get means it will download the file. Okay, get means it will download the file. Okay, so from where I have to download the file? I have to download it from HDFS, right? So root mr out space, sorry, file name. What is the file name? File name is part something, right? part, press tab. No, it is not showing. Let me check from here. So part hyphen 5 zeros. Part hyphen 5 zeros. 1, 2, 3, 4, 5 zeros. And space. So where I have to download this? So this file I have download to our current directory. Current directory is indicated by dot. So you're all getting this command, guys. HDFS, DFS, get is used to download the file. From where I'm downloading? From mr out, the file name part hyphen 0000 I'm downloading. So where I'm downloading to current directory. Current directory indicated by dot. So then I'm pressing enter. So once I'm pressing enter, guys, already we have that file. So part 000, it is already there. So I'll do one thing. I will remove this part 000 first. How we are going to remove, guys? RM. Oh, that is inside. No, that is inside. Okay, here only, right? So remove tab part, right? Okay, let me remove this. So it is removed, right? So let me check once whether it is removed or not. Yes, it is removed now. So now I'm going to run this command. So once I'm running this command, so it is downloaded. Now check with ls command. Check with ls -l. So now look at here, guys. Part hyphen 000 is present. No, it is not overwritten. I have not uploaded it. Okay, that was the old one. Okay, for everything it will take default name part hyphen 000 only. Okay. So now look at here, guys. Let me check the data output. So how we are going to show, guys? Cat part hyphen 000. Correct now? So this will show the output. Yes. So now I'm clicking on this. Look at the output, guys. So this is created automatically. Look at here, guys. Have you seen the magic? So many of them are asking, right, sir, what mapper will do, what reducer will do. Only the job is we have to write the function. That's all. So automatically it will create everything. So is this interesting? So this is how you are going to run your mapper and reducer code. So only the thing is you have to familiar with few commands. So now export text file to CSV file and then download, sir. So that is in CSV format only. Why we have to download? See, it is not allowing me to show the data, right? So that is inside HD Hadoop user. So cat command will show you the same thing. Otherwise, you can use nano also. By using nano also, you can display the data. Nano part 0. See, it is going to show the same output. Is it not showing the same output? It is showing the same output. Control X. Or you can use gedit also. Gedit. So whatever the command you know, editor command, by using that, I can view the data. When we have huge amount of data, then it will take output in different names. 0.0, see part hyphen 000, part see 0, and then it will take part 0001, part 0002, like that it will distribute the data. Okay, so you have to check one by one. What logic is used here for counting total transaction country specific? Okay, now look at here, guys. Somebody is asking the logic. So I will show you the code. So this is your program, guys. So I'm going to show you the code. Sales mapper, right? Okay, sales mapper.py. So this is the simple logic I've used here. Guys, I'm reading file. So from the system in, see comment, don't concentrate on comment. So if line dot start with transaction date, continue. So actually you have to see your data set. So in your data set, it is started with transaction data, right? Date, right? So then we have to continue. That is what it is showing. And then split the CSV line. So I'm splitting CSV line. I have written the same code. So I'm reading line wise. So line wise, I've taken line dot strip dot split. I'm performing split operation. Why I've taken comma operator here? Can anyone tell me why I've taken comma operator? Already I've told you, right? So once it is a CSV file, so it is comma separated. The delimiter used here is comma. So based on comma, I'm dividing it into what number of words. Is this clear? This code is clear. And next line, country is equal to, see, I'm taking the country. So where exactly the country is present. Look at, count the column 1, 2, 3, 4, 5, 6, 7. Correct? Now seventh column is country. So what I'm doing, I'm taking the what seventh column name. So field of 7 dot strip. That is the code I've taken here. And then, so that is stored inside, see, field of 1. So field of 1 means field. See, word we have taken here. So if any spaces are there means it will strip. That's it. So extra spaces are there means it will strip. Next, we have to emit this key value pair, right? So that we are performing here. Okay. So country, it has to show country and then product value it has to take, right? So product we have assigned with 1 actually. Okay. And then remaining all we are skipping and then we are coming out. So this is the code we have taken for mapper. Sir, can we take the code explanation in next class? Yes, definitely, Priyanka. Priyanka, I have not yet completed my syllabus. So I'm showing you the code, that's all. Okay, somebody asked me to show the code, that's why I'm showing. Okay, quickly I will show reducer concept also. Cat reducer. Otherwise, you can analyze by yourself, guys. Why I have to explain the code? You people can understand everything, right? See, this is the reducer code. See, from mapper, I'm getting input. The same input I've taken here. And so I'm performing addition operation here. Look at here. Somebody asked me, right? So where you are going to perform addition operation. Total count is equal to total count plus count I'm taking here. So based on country is equal to country. So once Australia equals to Australia means then I'm going to perform addition operation. So based on country name, I'm performing addition operation here. That's all, guys. This is the code I've taken. Guys, here so many hash symbols I've taken. So once we have removed all these hash symbol means, then we are going to get only minimum number of codes. So do we need to write the Python file code in practical exam? Of course, yes. Of course, yes. So all wondered, guys. All wondered. See, all these things I have shown you, right? So these are all I've shown you, right? This code and this output I've shown you. And this is covered. And this is covered. So everything is covered. So file system content. See, it is showing file system content also. That you can see here. So once you scroll up, see here, it will show file system content also. So once you are entering this command, so once again, guys, see, look at here. It is showing all the information. See, job counters, it is showing here. File system counters, it is showing here. See, each and every information. So mapper is started with 0 and ended at what 100%. See, every information it is showing. And you can track this information on this website also. 8088. That is the proxy server it is running. Guys, look at here. Once you have pressed this command, automatically it will do all the job. So this is the beauty of using this Hadoop system. Okay, yes. Okay, how many of them felt very happy by looking at Hadoop program? So how many of them felt very happy, guys? So in our HDFS lab, do we need to set up Hadoop cluster from scratch or setup is already there? Setup is already there, guys. But see what I'm going to tell you. So once everything is ready, then blindly you are going to put the commands, right? Blindly you are going to type the command. Suppose any type of errors you are getting means how you are going to encounter. So because of that reason, always I am going to suggest to my students, you people experience the installation. Guys, nowadays we have a chat GPT. By using that chat GPT, by using Stack Overflow, so we can install any software. Okay, so my suggestion is better you all install the software. So you have Ubuntu operating system means then it is very easy to install Hadoop software, guys. So you have Windows operating system means, so there also you have WSL option. By using that, you can install Hadoop on your system. See, like I have installed here. But yes, so once you are restarting your system, so every time I'm going to face the problem of SSH. That SSH you have to clear. So by using ChatGPT, I have done this. So even you people can perform this installation very easily, guys. So yes, is this clear to everyone? So still I have not covered all the syllabus, guys. So I'm left with a few more topics. So anyway, next class I'm taking extra class right there. I'm going to cover all these things. So this is a very, very easy concept. So only they have taken examples. That's it. So this I can cover in the next coming class. So, okay, we'll do installation. Thank you. Okay, yes. Guys, I have installed multi-node system here, but in what data node, I'm getting some errors. So that's why I've shown everything in a single node. Okay. So once we are using multi-node system, then you can experience how data node is distributed. Everything you can check there. So here, guys, one more thing I want to show you. See, once you are clicking on this, see here, you can see data node information. See, this is data node. See, we have installed only one data node here. So that's why it is showing 1 year. Okay. Look at here. See, this is the data node name. So this is the capacity of the data node. Okay, version of the data node. Everything is mentioned here. And look at here, guys. And one more option I want to show you. See, I have taught you about replication, right? See, look at here. This is the replication. Okay, once we are uploading data, so only one copy of data is stored in our single node. Suppose you have a 3 nodes means, so it will store 3 different replica of the data. Understanding my point, guys? This is the replication of your data. So by default, it will take 3 replica, but here at the time of installation, we have taken only 1 replica. That's it. Because to avoid data dependency. And size of this data is less than 128 MB. So this has taken very small size, guys. See, this is the maximum size. 128 MB is the default block size. Okay, this and all I will explain in the next coming class. Sir, will Java code be acceptable exam instead of Python? Yes, you can write program in Java also, but Java will take what? See, you have to write 100 lines of code. Sir, please share Python code also along with PPT. Definitely, I will share, guys. So on word count also, I'm going to share you guys. No need to worry. Okay, word count, we have a separate mapper program. So on sales, we have a separate mapper program. I will share you both. Okay. So have you felt today, guys? You all felt very happy? Sir, okay. Numerical question bank. So previous year, you go through the previous year question bank. Guys, see, since we are framing first time question paper, you cannot guess what type of question you are going to get, guys. See, numerical questions means it is very easy to solve. So you have to use the concept what I have taught. Based on that, you have to solve the numerical problem. That's it. Okay, so it is not like I'm going to take questions from a previous year question paper. Anything else you want to ask, guys? Guys, next Saturday, I'm taking extra class, guys. So let me type here. So either from 6:30 or 7:30, I'm going to take next class. 6:30 p.m. Saturday. I'm taking extra class, guys. Okay, because I have to cover 6th session concept. So that's why I'm taking extra class to complete the syllabus. Okay, next Saturday, guys. What is exam pattern? Numerical, theory, code, percentage, all. Mixture of all. Guys, I'm taking this subject the very first time. Previously, I was taking big data analytics. So big data system is very new to me. Okay, very first time I'm framing question paper. So you are going to get mixture of numerical, theory, and code. Okay. Number of question, it is going to vary, guys. So minimum 7, maximum 12. So each and every question will carry 1 or 2 marks. That's it. Is easy to pen paper test or computer based? It is pen paper test. It is a closed book exam, right? 5 to 7 or 5:30 to 7:30. I will try Himabindu. Okay, I will send a request to Vasusaini sir. So based on him, I'm going to fix the time. So we got email for computer based for EC2. Computer based, how come? See, you have to write an answer and then you have to upload your answer sheet. You all belongs to semester 1. Is this your first exam? Okay, yes. So you have to write answers on the answer sheet. Then you have to upload your answer sheets. Question wise, you have to upload your answer sheets. Better you all send a request to examination center, guys. So examination team. So they will provide you clear picture on examination. Ask them to take one orientation program. So how quiz will be taken? I think that is starting from tomorrow. Yes. So online. So you are going to get a message. So online you can take a quiz. The default mode of examination is on-site. So wherein the exams will be conducted at designated centers. Correct. See, one of your friend messaged according to the test demo recording. So there are 2 options available. We can either write by hand or type. Yes, you can type there on system. You can type. Better always take a pen and paper and write your answers. Yes, I've seen many people are going to type the answers, but sometimes we can't write. Okay, that is left to you guys. Total marks for EC2 is 30%. 30 marks. Guys, that partition already I've told you, right? That partition I already have told you, is it? So many time I've shown you that. So it is there in your handout, sir. So 30% for your MC2, sorry, EC2. So EC1 again 30%. And EC3, that is your final exam, for 40%. So here in EC1, quiz 10% and assignment 20%. 20 marks you are going to get in assignment. So this assignment I'm going to give you after your exam. After midterm exam, I'm going to release assignment. Okay, quiz you will be having 2. So 5% before your examination, midterm examination. After your midterm examination, you are going to get one more quiz. Okay. So after your midterm examination, you are going to get one more quiz. So assignment. So after your 10th session, after 10th session, I'm going to release the assignment. So is this clear? So assignment is purely lab based. It is purely lab based. That is on experiments we have given. So do we have to mobile? Do we have to take mobile to upload the sheets? You're not supposed to carry mobile. That and all you just ask the examination team, guys. What you have to carry, what you should not carry, everything they're going to mention, guys. So any doubts? So have you have understood today's concept, guys? You all enjoyed? You all enjoyed today's session? So last class, you people were asking, right? Sir, please look at the chat box. Okay, now I answered each and every question on your chat box. You all felt very happy? Hmm? So have you felt on today's session? Can you all quickly respond in chat box? So can you all give me one line feedback on today's session quickly? See, always you people are saying it is too much. Okay. So even it is too much for me also, right? Still, I'm not completing syllabus. So next class, I'm going to show you how to work with the Hadoop system, guys. Okay, Hadoop system, I'm going to show you in the next class. So some commands I'm going to show you. Some basic commands I'm going to show you in the next session. So that is more interesting. So see, once you are familiar with Linux, then it is very easy, guys. So it is same like your Linux commands. Thank you, Tanya. So do you have any document to set up Hadoop on your system? Actually, Ajit, do you have Ubuntu system or Windows system? What do you have? What do you have? RHEL. Okay, Linux operating system, right? Linux, under Linux, which software you are using? Which OS you are using? Is it Red Dot? Okay, Red Dot you are using, right? So then do one thing. You go to Google and you search the instructions for particularly your operating system. So that will give you everything. Okay. So for Windows also, guys, see, I used ChatGPT to install the entire software. So everything it will give you, guys. Only the thing is you have to copy the command, you have to paste the command. That's all. So 2 to 3 times you have encountered with the problem is then you will understand the complete architecture. Okay, with explanation, it will give you each and every instructions. My suggestion is always install Hadoop on your system. See, once you are installing Hadoop, by default, it will take mapper and reducer. Next, Hive, Pig, MongoDB, everything we have to install on top of that. That we can learn later. So right now, we have to learn Hadoop. Right now, we have to learn mapper and reducer concept. Okay, do we need to use more than one system? No need to use more than one system. See, you can create any number of virtual system, right? So in a single system, Ajit, see here, you can observe here. See here, I've created two what systems. See, once I'm clicking here, so this is my worker node. So Ubuntu worker node. So once I'm typing Ubuntu, so then it will show my master node. This is my master node. See, in a single system, I've installed two. So this is my master and this is my worker node actually. I have installed two virtual machine on top of my Windows operating system. See here, I've opened two terminal. So this is one system. You can check here. So host name, let me show you. Host name -I. So this is the IP address for my master system. So 172.18.100.25. And next one, so let me type here, host name space -I. See, this is showing another one. 172.1800. Is it showing same? Okay, I think yes. In SH, I have not changed it. So I have to change the IP address here. Even we can change the IP address also. That and all I have not done, guys. That's why I'm getting some errors. That I will clear later. So still I'm running everything on single node. So topics are wonderful and you are explaining it so awesomely. But even after stretching the class and taking extra classes, the syllabus is lagging. That means syllabus is too lengthy like regular classes and it is not aligning with the schedules. So since schedules have to be replanned. So next class, Ravi, definitely I'm going to replan it. So I'm going to reduce few syllabus. So as I told, since I've taken very first time, I did not see anything on the syllabus. I've started with my class. So because of that reason, I'm feeling it is too lengthy. So after completion of this course, so again, I'm going to take, right? On that time, I'm going to change the syllabus. On that time, I'm going to show you the syllabus. Okay. Okay, guys, that's all. So now the time is 9 o'clock. So almost 3 hours we have taken to complete the 35 slides. Okay, guys. Yes, next Saturday we can meet and let us try to complete the syllabus. Okay. Thank you all, guys. Have a nice weekend. So weekend is over. So have a nice night, guys. See you all. See you in the next session. Next session on Saturday and Sunday. Saturday, I'm going to cover 6th session concept. Sunday, I'm going to cover 7th session concept. Thank you all, guys. Thank you all. Bye-bye. See you.